so I want to wrap up the discussion about the dimensions. So we saw last time this trick. I had said, let's try this one. It's a little bit better. I had said there exists a very special modular form of weight 12 for SL2Z such that it is non-vanishing on the whole upper half plane. Of course, most modular forms, they don't vanish most places, but this one doesn't vanish anywhere. And its Q expansion starts off with Q, and the constant term is 0. As you go up to I infinity, it vanishes. And I'm even scaling it so that the leading coefficient is 1. But if I told you a priori that a modular form vanished at infinity, that doesn't mean it starts with a Q. Maybe it starts with a Q squared. It just means it doesn't start with a non-zero constant. This one has a simple 0 at infinity, or in terms of Q, a simple 0 at the origin as a function of the open unit disk. Okay. So we used this last time. We used this after proving the vanishing of the spaces of modular forms, after proving that these are 0 for negative weight. We used this to show that every modular form of weight 4 is a scalar multiple of E4. There's only one-dimensional space of modular forms of weight 4. And the trick that we use can be used more generally. So if you give me a modular form of any weight, let A0 be its constant term, its value at infinity, constant term of the Q expansion. So if you look at the difference, F minus A0 EK, that's a modular form of weight K, it's a vector space, and the difference at infinity vanishes, right? It's rigged, constant term 1, so this is constant term A0, constant term 0. And so therefore the Q expansion starts off with no constant term, and so if you divide it by delta, in terms of Q expansions, since this starts with the Q to the first, the ratio is bounded at infinity. Yeah. This is a simple 0 at infinity, and this has at least a first order 0. So therefore the ratio is okay, it doesn't blow up. And this difference is a modular form of weight K minus 12. It satisfies modularity for weight K minus 12, that's easy. And it's holomorphic on the upper half plane because delta doesn't vanish anywhere, and even at infinity, it's finite. So this is a modular form, and now we see we have an inductive process in place. If I call this then G, then I see that any modular form of weight K can be written as a constant times EK plus the modular form of weight 12 delta, the special one times G, where G is an NK minus 12. And this decomposition of a modular form, this guy is a modular form weight K, and this decomposition is unique. Why is it unique? I just have to be able to read off one of the terms and then the other one by subtraction.
Is there a restriction on K?
For any of these spaces.
Any of them?
Yes, of course some of them might be 0 spaces. Yes. In fact, K is negative. This was kind of our starting point. So I can read off A0 because if I look at this equation at infinity, at I infinity, this vanishes because the delta component vanishes. And that goes to 1. So you can in this decomposition, you can read off A0. And therefore this piece is unique, and therefore you can then subtract divided by delta to recover G. So this is a direct sum decomposition. So in the language of vector spaces, I can say I have a direct sum decomposition The whole space is a direct sum of the scalar multiples of ek, that vector space, plus the vector space nk minus 12, just multiplied by the function delta. And so therefore, well, okay, you asked about is there a restriction on the value of k. Of course, this makes no sense if k is 2. There is no E2. Well, okay, there is the E2. It's not a modular form. And also, there's no E0. But the whole point of this construction here was a modular form of weight k that starts with a 1. Now, if I'm in weight 0, I could have used the constant function 1 in place of this. And an argument still would have worked. So maybe I should say this is for k greater than 4. And then for k equals 0, m0 is c, direct sum delta times m minus 12, but we know that that's 0. So the modular forms of weight 0, this just dies. And so modular forms of weight 0 is constants. And then we have, for k greater than 4, we have this decomposition. And so what we can then say is the dimension of mk is 1 plus the dimension of mk minus 12. So this is the correct version of that screwed up recursion I was trying to describe last time. For k, let's say greater than or equal to, where this, well, I guess I could say for k greater than 4, because that's when these isosceles theories start existing. Yeah? And so therefore, I have a recursive formula for my dimensions. The only catch is, if you try to apply this when, so for instance, if k is less than 12, we know that that's dimension 0, so we can read off the dimensions of the low spaces of modular forms below weight is one-dimensional, except when k is 2, I don't really have a valid equation here. So you can look in the lecture notes to see why m2 is 0. The proof is, basically, if you have a modular form of weight 2 and you square it, you get a modular form of weight 4. And we already know the space of modular forms of weight 4. And then you can just do some trick by looking at it at the number I to read off that it actually has to be 0. Right? So you can stuff m2 into m4 by squaring and then do some little bit of algebra to see that knowing what m4 is, you can then read off m2 as 0. So this equation, so now that we know m2 is 0-dimensional, then we can use this equation to recursively compute the dimensions, that formula that I gave you before. I want to stress something though. Why do I need to use ek? Only because it has the property that it's a modular form of weight k that has value 1 at infinity. But I could give you examples of that without using ek. I could just use e4 and e6. So somebody give me a big even number.
42.
42. Ha ha ha. Okay. So we do not need. So I'm just going to kind of, so this dimension quota implies that you get the general formula for the dimension of mk, and I'll say here, including k equals 2, that needs a special consideration that I'm not writing out here. But this recursion is really the key idea. So we do not need ek for k greater than or equal to 8 in this proof. It seems that I'm using the EKs, but we just need, in each of these MKs, some modular form whose value at infinity is 1. And the EK is just a convenient choice. But I can find such an F just using E4 and E8 powers of those. So for example, take k equal 42, then all I have to do is write this as a multiple of 4 plus a multiple of 6 with non-negative coefficients. And since it's not divisible by 4, that means it's 2 mod 4. So if I just subtract 6 from that, I get 36. So I get 4 times 9 plus 6 times 1. And so I could use E4 to the 9 times E6. In case k is 42, in place of E42. These are not the same modular forms. Yes, they both start with a 1, but I mean, it's a highly non-one-dimensional space. It's not a one-dimensional space. So we saw that in weight 12, right? E12, E4 cubed, E6 squared. are all modular forms of weight 12 that start with a 1. They're not the same after that. So I could get away, this illustrates what you can do, and again, it's a 9, it's not a Q. I can do the same thing in every weight above 8, every even number greater than or equal to 8 can be written like this. Of course, in multiple ways, but just once is enough to give this argument to split off a one-dimensional space so that then when you take the dimension equation, you can then not pay attention to it anymore, it's just left with a 1. So in fact, the number of ways, turns out, the number of ways of writing an even integer k for even k greater than or equal to 0, is it true in case 2? Is it even true in case 2? In case 0, I can write this in one way, 0, 0. In case 2, I can't do this. Okay? In case 4, I can do it in one way. In case 6, I can do it in one way. In case 8, I can do it in one way. In case 10, I can do it in one way. In case 12, I can do it in two ways. These numbers are the dimensions of the mk's. This number of ways of writing an even non-negative integer in this form is actually equal to the dimension of mk that we've already computed without having to know this fact. Right? We just needed one example and we can compute the dimensions. And so therefore, this actually winds up implying that mk has as a basis all the products E4 to the A, E6 to the B, where A and B are non-negative, and 4A plus 6B is K. That makes this a modular form of weight K. This implication is not immediate. That just means that this set has that size. But why is this a linearly independent set? You have to prove that too. They are linearly independent. Okay, that requires some argument. You can use the trick that one of these vanishes, one of E4, E6 vanishes at I, the other vanishes at the cubic of unity in the upper half plane. To read off a linear relation among these things has to have 0 coefficients from inductively. So this set has the same size, lies in the space, is linearly independent, and has the same size as the dimension that we already computed. So here's a basis. We actually never need the EKs to get the basis of this for k greater than 6. If I never mentioned anything but E4 and E6, we could have gotten to this point. All right. So in fact, it turns out that every modular form is in fact a linear combination of the powers of E4 times E6. E4 and E6 generate all the modular forms. Yeah. Are there other generators? Well, sure. I mean, you just. Well, I mean, so, okay, good question. The question is, are there other generators? So here's a property. So a nice feature of this basis is all the coefficients are rational. Right? Because we knew about zeta 4, the formulas for zeta of 4 and zeta of 6 as powers of pi, multiples of pi to the 4 and pi to the 6, and we normalized it. We saw the coefficients of these are rational, so the powers, everything is rational. And that's very convenient. So for example, as a consequence, a corollary, maybe I'll actually move this over here. A corollary of that fact, and then I'll address this question about, are there other useful bases besides this one? And in fact, there is other useful examples. But let me show you a consequence of this. So a corollary of the fact that E4 and E6 have Fourier coefficients that are all rational, and hence the basis is a basis of modular forms with entirely rational Fourier coefficients. A corollary of this fact is that if you have a modular form of weight k, positive weight, we're not interested in constants, and you write out its Q expansion, and all the coefficients are rational beyond the constant term, then the constant term must be rational. Okay? This is a non-trivial fact. What is it saying? It's saying if you have a modular form, some weight, and you know something about its non-constant Fourier coefficients, that they're all rational, the constant term must also be rational. And the proof is in the notes. The proof uses the fact that there's a basis of modular forms in weight k with entirely rational Fourier coefficients. And it also actually needs the axiom of choice. It requires theorems about extending field automorphisms up to from number fields up to the complex numbers. So you need the axiom of choice to extend those. So there's part of this is analysis, getting the basis, and part of the proof is abstract algebra about field automorphisms of the complex numbers. And of course, the only field automorphisms you know of the complex numbers are the identity and complex conjugation. But that doesn't mean those are the only ones. If you believe the axiom of choice, everyone should believe the axiom of choice, then in fact there are a gazillion more, but you can't write them down by a formula. But they're out there and you can use them to prove this fact. Now you might think, well, who cares? So here's an interesting use. Let me show you a corollary of the corollary. So again, we never needed the EKs for k above 6. So we can pretend that we never talked about them. So here's a corollary. For even k greater than 8, zeta of k over pi of k is a rational number. So I'm going to prove this using modular forms. I can't prove this for k equals 4 and 6 because I'm going to need the E4 and E6 have rational coefficients to get this corollary, and that was based on zeta 4 and zeta 6 being known to have irrational multiples of pi to the 4 quadratic. And I'm not going to get it for k equal 2 either, the most famous example, pi squared over 6. But anyway, we'll get it for the other ones. How? So recall the Eisenstein series has the Q expansion which does not require any knowledge of special values of zeta functions to derive this fact. Okay? So this was the Q expansion of the Eisenstein series. So the proof was that for even k actually greater than 4, this was the Q expansion of the Eisenstein series. So this was a point. This is a modular form. And previously, how did we normalize this Eisenstein series? We divided by the constant term in order to make the constant term 1. Right? And then we actually stated the explicit formula for zeta of k to see the EKs all have rational Fourier coefficients. But ignore that. Pretend you never knew that. Okay? We derive this without knowing anything about special values of zeta of k. And now, rather than normalize this by using our knowledge of a formula, Euler's formula for zeta of even numbers, and dividing by the constant term, let's instead divide through by this number to normalize this so the coefficient of q is 1. Okay? And so what this tells us is gk of tau, if you divide it by 2 pi I to the k over k minus 1 factorial, so if you divide by that number outside this summation, the 2's will cancel, and you'll be left with 2 pi I to the k over k minus 1 factorial as the constant term plus this. Now this is a modular form. You just scaled the modular form. You still have the modular form, weight k. But the coefficients here are manifestly rational. They're actually integers. Okay? So since these coefficients are the non-constant Fourier coefficients are rational, we get the constant term has to be rational. And of course, the 2 is rational, the I to the k is even, k minus 1 factorial, and so that implies zeta of k over I to the k is rational. And again, just for emphasis, for even k at least 8, right? It would be circular to deduce this for k equals 6 or 4 because we needed this fact to get the rationality of those Fourier coefficients to prove that corollary up there. Okay? So this is kind of an amazing proof that the zeta function of even integers, at least 8, is a rational multiple of power of pi. How do we prove it? Because up to a rational number, this occurs as the constant term of the Fourier expansion of some modular form in which all the higher coefficients are trivially rational. And this argument, which is a much more complicated proof that this ratio is rational, is really useful because there are other zeta functions in the Riemann zeta function. There's zeta function of number fields, zeta function of q joined over 2, zeta function of other fields besides the rational. So the zeta function, Riemann zeta function is like the zeta function of the rational numbers. And so you can ask, what about the values of these other zeta functions at special integers, at even numbers, for example? And so it turns out this is a very similar theorem for zeta functions of other number fields, totally real number field, don't worry about it. But there's a very similar rationality property of zeta values for other types of zeta functions, and the proof is based on constructing a more complicated generalized type of Eisenstein series in which this type of a ratio using more general zeta functions occurs to the constant term of the modular form whose higher Fourier coefficients are trivially seen to be rational. And thus, these much more mysterious zeta values are, have rational ratios with powers of pi, well, times some square root. But anyway, but there's a generalization of this result proved by this phenomenon that special values of zeta functions essentially arise as constant terms of modular forms. Okay? And so that's pretty neat that you can use this idea to get that information. But this does not tell you anything about what those rational numbers are. And it's like, oh, it's rational, but like what rational? Euler told me it's a Bernoulli number times stuff. So this is a much more qualitative result, and it's kind of amazing. You can prove that certain numbers are rational by constructing them as constant terms of Fourier coefficients of modular forms. Coming back to the question, though, about are there other convenient bases or useful bases? So this is not the best basis in the world for other purposes. Because look at this corollary. I said that if all the coefficients are rational, the constant term is rational. Now, you might say, well, what about if all the coefficients are integers? Is the constant term an integer? That's false. Take like E4. Sorry, maybe I should point this out. Right, E4 start off with 1 plus 240 summing whatever sigma 3n q to the n. And so if you look at 1 over 240 E4, that's 1 over 240 plus the sum. And so you can just see by simple examples, all the higher things are integers. It doesn't mean the constant term is an integer. Well, it is rational, consistent with the corollary. It's not a false statement. So, in terms of the other convenient bases, you see, you can also use this basis to show that if a modular form of some weight has all rational Fourier coefficients, it must be a rational linear combination of this basis. But if a modular form has all integral Fourier coefficients, it does not have to be an integral linear combination of that basis. Even though E4 and E6 have entirely integral Fourier coefficients, so their powers and products do as well, it's not sort of an integral basis of the space of modular forms of weight k with integral Fourier coefficients. So you might see other bases with integral coefficients for which all the modular forms of that weight with integral coefficients are integral combinations of those. And so there are bases like that. Essentially, you use powers of that delta modular form in place of one of E4 or E6, and then you can get it. So there certainly are reasons you might be interested in kind of integral bases for modular forms in some sense. Yeah, so anyway, so that's kind of a surprising consequence of developing the whole theory. Now, I was going to say something about the construction. I just sort of said, well, there's a special modular form delta with these properties, but I really want to get to something else, so I'm going to have to pass over, in unfortunate silence, the construction. It's written in the notes how you build a special modular form with weight 12. There are many ways you can do it. I'll just say that in the notes, I construct it as using Poisson summation, some special infinite series, and then use some estimates to prove it doesn't vanish anywhere. So there are many approaches to computing dimensions and spaces of modular forms. The way that we've done it with this special modular form delta is in some sense a hack, because if you look at modular forms for other groups, they usually don't have some modular form out there that vanishes only at infinity with a simple zero. This is kind of the key point, and we can use that to divide by it to get these recursive properties. So in general, you don't have an analog of the delta for modular forms in other groups, and so you really need to use more sophisticated ideas, Riemann-Roch theorem, and other things to compute these dimensions. So the way we did it here is elementary as things go, but is not the way that you can compute dimensions of spaces of modular forms on other groups in general. You need fancier ideas from, say, algebraic geometry or other things, and other interpretations of modular forms to make those calculations. But here you can sort of do it with your bare hands, granting the existence of this kind of special modular form delta that actually we're going to come back to delta, in fact, right now. So maybe I really should say something about where it comes from, otherwise stuff really seems to come out of nowhere. So I'm just going to explain where delta comes from, and then we're going to mention some surprising properties of it. So how to build this modular form delta of weight 12. It doesn't vanish anywhere in the upper half plane, and as a function of e to the 2 pi I tau, it starts, the constant term starts with q. No constant term, its q expansion starts with q. And so the way it comes about is it's going to be a power of some other function. So let theta of tau. So this is going to look like it's coming out of nowhere. Well, it is. From our perspective, it's coming out of nowhere. Sum over odd integers, minus 1 to the n minus 1 over 2, n e to the pi I n squared tau over 4. Okay? So there's an infinite series for you. So let's orient ourselves here. So tau is in the upper half plane, x plus I, y. And I'm multiplying by I, so the real part of this involves minus y, and y is positive here in the upper half plane. This is rapidly convergent in the upper half plane. And so it turns out, if you're careful, when you replace tau by tau plus 1, it transforms not by being equal, but it's off by an 8th root of unity. So the 8th power transforms nicely. Okay. And if you use what I'll call a twisted Poisson summation formula, then this one I'm going to have to pass over in silence, but it's some kind of generalized Poisson summation, you can show that under minus 1 over tau, it transforms, the eighth power transforms by a factor of tau to the 12th. So, and clearly, so let's write out, let's get our bearings here. It starts off with e to the pi I tau over 4. Then it's minus 3 e to the pi I 9 tau over 4. Plus 5 e to the pi I 25 tau over 4. And so on. See, it starts off, there's no constant term. This thing goes to 0 as tau goes off to infinity. It doesn't start with a constant. The n equals 0 term's not there. It's something we're odd again. And so it's holomorphic, converges is holomorphic, and has these two properties, and goes to 0. And so the net conclusion is the 8th power is a modular form of weight 12, and so this is the delta function. Okay? For tau in the upper half plane, I'm going to define delta of tau to be the 8th power of this other holomorphic function. And so you can see that it transforms like a modular form of weight 12. Right? Delta of tau plus 1 is delta of tau, and delta of minus 1 over tau is tau to the 12 delta of tau. And it vanishes at infinity. Right? This guy vanishes, then you take the 8th power, And now I need to get the Q expansion. Well, you just take the 8th. I know this is a power series in e to the pi I tau over 4, but the 8th power is equal under tau goes to tau plus 1, so the 8th power will have to be a power series in e to the 2 pi I tau, not just e to the pi I tau over 4. But in fact, we can figure out how it starts by just computing e to the pi I tau over 4 minus 3 e to the pi I 9 tau over 4 raised to the 8th power. What's the first term? It's just the 8th power of that, which is e to the 2 pi I tau plus the higher stuff. Okay, so the only catch is it's not at all obvious that this thing doesn't vanish on the upper half plane. Okay, and so I'll just say to show that this thing doesn't vanish on the upper half plane, forget the delta, go back to that function theta, show this doesn't vanish on the upper half plane. And how can you do that? Well, if this were to vanish, well, let's put it this way. If a modular form vanishes somewhere, if you think about the modularity condition, it's going to have to vanish at every point in its SL2Z orbit, because of f of a tau plus b over c tau plus d is some c tau plus d to the k times f of tau, and c tau plus d's never vanish, because tau is imaginary and d and c are real. So if a modular form vanishes anywhere, it'll vanish at the whole SL2Z orbit at that point, and so it'll vanish at a point in the fundamental domain. So if you wanted to prove that a modular form doesn't vanish anywhere in the upper half plane, it suffices to study it on the standard fundamental domain, which is bounded away from the real axis. Very convenient. And so I'll just say it suffices to show that the function theta doesn't vanish on the fundamental domain, which would make delta not vanish on the fundamental domain, which would make delta not vanish anywhere. And you could just use an argument by contradiction. If this vanished, you could move the first term over to the left side, take absolute values, and do a little bit of estimating, and you just get a contradiction. If you're plugging in a point in the fundamental domain whose imaginary part is like at least root 3 over 2, right? The height of the cubic unity, those are the corners. Then you get a contradiction. So this is written up in the notes. So it's just proof by contradiction. So it's a very analytic proof. It's a very analytic proof. You can. There are other ways of proving the non-vanishing using ideas from algebraic geometry. But in any case, I'm not going to give the details either way. But upshot is, so this is the discriminant, the special modular form of weight 12 that has a simple 0 at infinity and doesn't vanish on the upper half plane. So in fact, if you expand this out, you see this guy has integer coefficients as a power series in e to the pi I tau over 4. So when you take the 8th power of it, it will still have integer coefficients. So delta's Q expansion is going to have integer, take the 8th power of this